Okay, so in this problem is a circuit problem, and the problem says to consider the circuit diagram below. All right, so it says values of various components are given. So our E1 here represents the voltage of battery 1 over here, and our E2 here represents the voltage of battery number 2 over here. And then the R's are all the resistance values, right? So R here, R5, 4, 1, 2, and R3. Now it says to find the values of the currents I1, I2, and I3 flowing with respect to the directions indicated in the circuit diagram. So whenever you're solving circuit problems, one of the most important things that you should pay attention to is the polarities of the different elements, right? Now, one of the main elements you want to identify its polarity is the battery, right? So the battery sort of tells you what direction you should expect the current to flow, right? So if you look here, battery number 1, its positive terminal is facing downwards, going this way. And same idea with battery number 2, okay? So this means that we expect the current to flow this way, right? So current is going to flow this way around this loop. And if in the process of finding the currents, we happen to get a negative current here, well, then that means that our initial assumption was wrong and that the current was actually flowing in the opposite direction. Same idea over here, right? So let's start by writing down our first step, right? So our first step to solving this problem is going to be to actually apply a rule called the junction rule. And I'll explain what I mean by the junction rule in a sec. So we're going to say step 1 is to apply the junction rule. Okay. Now, the junction rule states that if you look at a junction in a circuit, right? So a junction is sort of like a connection between multiple wires. If you take a look at a junction in the circuit, the sum of all the currents going into that junction is equal to the sum of all the currents flowing out of that junction, right? So for example, if we look at this junction down here, notice that we have current 2 and current 3 flowing into this junction, right? But at the same time, we have current 1 flowing out of that junction, okay? So what this means is that current 1 must be equal to current 2 plus current 3, right? Both currents are flowing into the junction, and we have a resulting current coming out of the junction. So this is actually the reasoning that we're going to use to write down our first equation. Okay, so we're going to say, for our first equation, we're going to say current 1 must be equal to current 2 plus current 3. Okay, so we're going to come back to this equation, but it's important to keep this one in mind. So our second step involves applying what's called the loop rule. So we're going to say step 2 is to apply the loop rule. Okay. So what exactly is the loop rule? Do you have any sort of idea of what it could be?
Loop rule. Let's see. Goes like that.
Okay, so to give you a hint, right, you see how the junction rule has to do with current flowing into a junction?
So it deals with voltages?
Right, the loop rule deals with voltages. Exactly. So the loop rule is actually a statement of, well, honestly, both rules are a statement of conservation of energy, but the loop rule says that if you start at any point in the loop or in a loop of a circuit and you go around that loop, right, then your total change in your potential or your total change in your voltage is going to be equal to 0, right?
So every time it goes through something, it's going to go through a voltage drop, and it has to
Right,
equal to the voltage of the battery before it splits.
right, exactly. You can choose any point in the, well, first you have to choose a loop, right? Because this
Yeah.
circuit is made up
Yeah.
of multiple loops. Also, the overall circuit is a loop, right? But let's say we're going to start with this loop over here. We'll call this loop 1. If we start at any point in that loop, we're going to be starting at a certain potential or a certain voltage, right? So say we start, let's say we start over here, and then we go around this loop, okay? By the time we come back, we're going to be at the same position, so our total change in potential is going to be 0. Now, the important thing to keep in mind when you're doing the loop rule is that as you go from the negative to positive terminal of a battery, your potential is going to increase. Think of the battery as sort of like a pump, right? So it pumps your potential up. However, as you go across a resistor in the direction of current, your potential is going to decrease, right? So that's the reasoning we're going to use in order to set up our equations. So we're going to say at loop 1, so at loop 1, right, we're starting at this point here, right? If we move down the circuit, we're going to have to go from negative to positive along our battery. So our potential is going to increase by the amount of voltage of this battery, right? Which is 18 volts. So at loop 1, I'll just write it in symbols for now, and then I'll substitute the values in. So we're going to increase by E1. And then as we go across R3, our potential is going to drop. And do you remember the formula we apply for potential drop across a resistor?
E equals I times R, so it's going to be negative. Negative
Right,
I. Yeah.
right, exactly, right? So we're going to apply Ohm's law. Ohm's law
Yeah.
says voltage equals current times resistance. So we're going to say E minus I2 times R3. So this is going to be I2 R3. Okay, so no resistor here, but look, we have a resistor here, right? So what's our voltage drop there?
I1, negative I1, R1.
Right.
Yeah.
And what about here?
Negative I2, R2.
Hmm? Okay, and then we return back to the same position, right? So this means that our total potential change is 0,
Zero.
right? So initial minus all of these drops must be equal to 0.
Yeah.
Okay, so let's substitute the values in. So E1 is 18 volts. Now I2, we have I1 here. I'll write the I1 first. R1 is 6 ohms, right? So we got 6 I1. And then we have I2 R3, I2 R2. So we have to add the R3 and R2. So this comes out to be 3 ohms. So this would be 18 minus 6 I1 minus 3 I2. So this means our first equation can be written, or this is actually our second equation. So our second equation can be written as 6I1 minus 3I2. And this is going to be equal to 18.
It should be plus 3.
Oh, thanks for that. So this is going to be 6I1 plus 3I2 is equal to 18. Okay, so far so good. Now let's move to step 3. So step 3 is again going to be an application of the loop rule. All right, so here we're going to apply the loop rule to loop number 2. All right, so over here we applied it to loop 1. Here we're applying it to loop 2. Okay, so can you help me set up the equation for loop 2?
It's gonna be the battery is 36 volts.
Mm-hmm.
It's going counterclockwise, so it hits the first voltage drop at it's gonna be I3 times R5.
Okay, so now is it going to be positive or negative?
It should be negative.
Right, because we're going in the direction of the current. So that
Yeah.
means we have a voltage drop here. So this is going to be minus I3 times R5. Okay, and what else?
Then it's gonna be minus I3 R4.
Okay, right, so minus I3 times R4. Okay.
Next one is minus I1 R1.
Mm-hmm. Minus I1 R1. And this should all be equal to 0. Okay, so let's substitute all of our values in there. So you said E2 was 36. Are there any like terms we can combine?
I3.
Okay, so we got I3 here. So we're going to have to add R5 and R4. So that's 1.5 plus 0.5, that's 2. So this would be minus 2
I3.
times I3. And then I1, R1, right? So this is 6 ohms times I1 equals 0. Okay, so our third and final equation is going to be equation number 3. We have 6I1 plus 2I3 is equal to 36. Okay, so this is good because we had 3 unknowns and we've managed to create 3 equations, right? So these are the correct number of equations we need to solve for I1 and I2 and I3 as well. So this is nothing more than just a system of linear equations, right? Now, do you have any ideas on how we can use some of the methods for solving systems of linear equations?
You could use the junction rule and plug it into solve for one of them, or you could just use a matrix to,
Mm-hmm.
just to solve for all of them.
Yeah, right. So it's a bunch of different ways. We can do the substitution method, right? We can solve for one equation, plug into another, plug into another one, and just keep that process going until we get our variables. We can also use the elimination method.
Yeah.
We can create a matrix and do Gaussian elimination, right? But we'll keep things simple for now. What we're going to do is we're going to take one equation, substitute it into the other. That way we have another equation. And then we can use the remaining 2 to solve for one of the variables. So let's start by substituting equation 1 into equation 2, right? So let's write that down here. We're going to sub equation 1 into equation 2. And what would we get if we did that?
Equation 1, solving for plug I1 in there. So it's gonna be 6I2 plus 6I3 plus
Right.
2, so 18.
Right, so we're going to do 6 times I2 plus I3, and then plus 3I2. So this is going to be equal to 6I2 plus 6I3 plus 3I2. We can combine the like terms here. That way we have 9I2 plus 6i3. And equation 2 says that should be,
18.
yes, equal to 18, right? Okay, so we're going to come back to this in a sec. Now, let's look at equation number 3. Is there anything we can do between equation 1 and equation 3 to help us solve?
Well, you can solve for I1. Just plug in I1.
Mm-hmm. Right, so if you look
Yeah.
here, right, we can take equation 1 actually, also substitute that into equation 3. That way we end up with another equation in terms of I2 and I3, right?
Yeah.
Okay, so let's do that. So we're going to substitute equation 1 into equation 3. And in this case, we're going to have 6i2 plus 6i3 plus 2i3. Combine like terms, this comes out to be 6i2 plus 8i3. And equation 3 says that should be 36. Okay, so now we have two equations in terms of I2 and I3, which is good because we can use those two to help us solve for I2 and I3, right? Now, how would we go about doing that? What would be our next step here?
Can line them up and yeah.
So
Yeah.
let's do that. We're gonna line them up. We're gonna put, let's go ahead and put this first equation up here. I'll write it in a different color. So we got 9i2 plus 6i3 is equal to 18. And then we have 6i2 plus 8i3 is equal to 36. Right, and here we can apply the elimination method to get rid of one of the variables. Which means that since these are not the same coefficients, we need to first choose which variable we want to eliminate and then multiply its equation by the correct factor so that we have same coefficients in the column, right? Okay, so let's say for example, let's say we want to solve for I2 first, right?
Divide the first one by 3 and divide the second one by 2.
Okay, so divide first one by 3.
Yeah.
If we divide the first one by 3,
Yeah.
that
Uh,
means we'd get a,
oh, you gotta divide the second one by -2.
right, exactly, right? So we're going to say I'll multiply the first one by 1 over 3, so divided by 3. And then I'll multiply the second one
By
by,
negative.
right, negative 1/2, right?
Yeah. -1.
Okay, so this is fine, but this will actually allow us to solve for I3, right? Because I2 will be eliminated. But that's okay because we can take I3, plug it back in, and get I2 as well. So let's go ahead and do the multiplication. So this first line here, what's that become?
3i2 plus 2i3 equals 6.
Okay,
The second one is negative 3i2,
mm-hmm.
negative 4i3,
Right,
negative 18.
right. Okay, so let's add everything up here. So this is going to cancel out.
Negative
Um,
negative 2i3
right, so we're going to have negative 2i3,
and negative 12.
negative 12.
And you can just divide by -2 on both sides to get
Right,
6 for 6i3.
right. So I3 here, and what would our units be?
It's current, so it's not ohms. Amperes.
Amperes, right? So we're going to have amps here. Okay, good. So we have I3. So what can we do with this?
Could plug that into, let's see, one of the previous equations to get. Yeah, you could plug it into that to get I1.
Right, so we can sub I3. And where are we going to sub it into?
Equation 3.
Okay, so we can sub I3 into equation 3 for I1. Okay, so this means we're going to have 6I1 plus 2 times 6 equals 36. And what does this give us for I1?
Okay. On the right side, it's going to be 24. On the left, it's going to be 6I. Divide by 6 on both sides, it's going to be 4.
Right, so I1 is going to be 4 amps. Okay, good. So now we have I3, we have I1.
And
We
you could
just need I2.
go back to original one to get I2.
Mm-hmm. So we're going to sub I1 and I3 into equation 1 for I2. Okay, so let's take I1 and I3, right? So I3 is 6, I1 is 4. Substitute that into equation 1 over here to solve for I2. So we're going to say 4 is equal to I2 plus 6, which means that I2 must be negative 2. Okay, so remember, when dealing with circuits, anytime you get a negative current, it just means that the current is flowing in the opposite direction you initially expected.
Yep.
So if you look at these arrows here, right, for I2, all this means is that I2 is actually flowing this way, right, at 2 amperes. Okay, so that's the end of the problems. Thanks again, Larry, for helping me out with this. So do you have any questions about this problem?
No problem. No
Okay,
questions.
good, good. All right, so thanks again, and I'll let you know how the tutoring process goes.
Oh, you stopped the recording already?
Now I am.
So now you got to cut this part out.
Yep.